Welcome to my 42nd tutoring session in A-level chemistry. In this video, I'll discuss the different types of hydrogen bonding and also explain the impact of hydrogen bonding on the physical properties of molecules. Please take a moment to watch my previous videos on topics hydrogen bonding, factors affecting hydrogen bonding, and the impact of hydrogen bonding on the physical properties of molecules. These three videos will provide you with a better understanding of this video content. Link to the videos given in the description below. Please do watch the videos. This video is continuation of the previous video on the topic impact of hydrogen bonding on the physical properties of molecules. Don't forget to subscribe my channel, share, like, comment and watch the full video. Hydrogen bonding influences the physical properties of molecules like melting point, boiling point, solubility, viscosity, vapor pressure and surface tension. There are two major types of hydrogen bonding that influences these physical properties. They are intermolecular hydrogen bonding that occurs between the molecules that leads to high melting point of substances, and intramolecular hydrogen bonding that occurs within the molecule leading to low melting point of organic substances. Let me begin my session with the impact of hydrogen bonding on melting point. What is melting point? Melting point is the temperature at which a solid substance changes to a liquid at normal atmospheric pressure. In most of the cases, you will find electronegative oxygen and nitrogen atoms engaging in hydrogen bonding, and they tend to interact with the electron deficient hydrogen atom with a partial positive charge, that is covalently bonded to a electronegative oxygen or nitrogen atom. Now in case of para-nitroaniline, you will find high melting point range of 146 to 149 degrees Celsius, while in case of orthonitroaniline, you will find low melting point of 69 to 71 degrees Celsius. Now this difference in temperature is due to, or it's because of the nature or type of hydrogen bonding in each compound, and is influenced by the arrangement or positioning of the functional groups on the benzene ring. And the arrangement or positioning of the functional groups on the benzene ring results in difference in the melting point between orthonitroaniline and para-nitroaniline. If you observe the structure of para-nitroaniline, you will find that the amino group and the nitro group are para to each other, while in case of orthonitroaniline, the amino group and the nitro group are ortho to each other. That is to say, they are in close proximity. And because of the close proximity of the amino group and the nitro group in case of orthonitroaniline, they tend to interact with each other, resulting in intramolecular hydrogen bonding. So you find intermolecular hydrogen bonding in case of para-nitroaniline, as the nitro and amino groups are far apart from each other, that is to say they are para to each other. But in case of orthonitroaniline, they tend to undergo intramolecular hydrogen bonding as they are in close proximity. So intramolecular hydrogen bonding, it occurs within the same molecule, and less energy is required to break this hydrogen bond, and therefore this results in a low melting or boiling point. While in case of intermolecular hydrogen bonding, it occurs between the molecules, requires more energy to break the bond, and this results in a high melting or boiling point. Likewise, in case of para-hydroxybenzaldehyde and ortho-hydroxybenzaldehyde, once again here the difference in the melting points is due to various types of hydrogen bonding that occur in each compound. and highlighting the critical role these interactions play in determining their physical properties. That is the melting point. So orthohydroxybenzaldehyde has a low melting point as compared to para-hydroxybenzaldehyde. In case of para-aminobenzoic acid, because of the distance between the carboxyl group and the amino group, they tend to undergo intermolecular hydrogen bonding. That is to say, the carboxyl group and the amino group are para to each other. While in case of orthoaminobenzoic acid, because of the close proximity of the amino group and the carboxylic group, they tend to interact by hydrogen bonding. And in case of paranitrophenol, because of the positioning of the functional groups para to each other, they undergo intermolecular hydrogen bonding. Well, in case of orthonitrophenol, because of the close proximity of the hydroxy and the nitro group, they tend to undergo intramolecular hydrogen bonding. So when you compare and contrast these four examples, you'll find that the functional groups that are in close proximity, they tend to undergo intramolecular hydrogen bonding, as you have seen in case of orthonitroanilin, orthohydroxybenzaldehyde, orthoaminobenzoic acid, and orthonitrophenol. While you come across intermolecular hydrogen bonding in case of paranitronilin, para-hydroxybenzaldehyde, para-aminobenzoic acid, and paranitrophenol. So the nature of the type of hydrogen bonding in each compound is influenced by the arrangement or position of the functional groups on the benzene ring, resulting in the difference in the melting points. What about the impact of hydrogen bonding on the boiling point? Now, boiling point is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. Now, water and alcohols have a high boiling point due to dipole-dipole interaction, that is hydrogen bonding. Now, the boiling point of water is greater than that of alcohols like methanol, ethanol, and propanol. The reason being, the water molecule can participate in hydrogen bonding and can hydrogen bond with four other water molecules. And water freezes at 0 degrees Celsius, and water turns to ice as it freezes. Now, ice tends to melt at temperature greater than 0 degree Celsius. As the temperature increases, the ice tends to melt and gradually turns into liquid. And at higher temperature, water boils at 100 degrees Celsius, and at this particular temperature, you'll find the individual water molecules escape into the vapor phase. Now, the heat energy, that is thermal energy provided by the heat, it weakens the hydrogen bond, ultimately disrupting the hydrogen bonding interaction, and ultimately breaks the hydrogen bond. And thereby, when the water boils, the hydrogen bonds are completely broken and the individual water molecules escape into the vapor phase. Now, what about methanol? Now, you will see that the methanol molecule can form hydrogen bond with two other molecules. So, water molecule can participate in hydrogen bonding with four other water molecules, while alcohol, that is methanol, it can participate in hydrogen bonding with two more water molecules, methanol molecules. So that is why methanol boiling point is around 65 degree Celsius. So the difference in the boiling point. So though the bonding energy or the bond energy is one and the same. So both in case of water and alcohol, the bond energy is one and the same, that is 21 kilojoules per mole of energy is required to break the bonds. Hydrogen bonds both in case of water as well as alcohol molecules. So though the bond energy is same, why the difference in boiling point? So the difference in boiling point is because of the extensiveness of hydrogen bonding. So hydrogen bonding is more. There is a number of hydrogen bonds formed in case of water molecule is 4 as compared to only 2 in case of methanol. So because of the extensiveness of hydrogen bonding in case of water molecule, the boiling point is more as compared to methanol. Now boiling point of alcohols are higher than amines of comparable mass, and this is due to the greater electronegativity of the oxygen atom in comparison to the nitrogen atom. Electronegativity of oxygen is 3.5 on the Pauling scale, and nitrogen it is 3. As I already mentioned, water molecule can participate in hydrogen bonding with 4 other molecules, while in case of methanol, it can interact with 2 other methanol molecules. So while in case of methylamine, you'll find the bond energy is less. So only 13 kilojoules per mole of energy is required to break the hydrogen bonds between the methylamine molecules. So water can form 4 hydrogen bonds, methanol can form 2 hydrogen bonds, and methylamine can also form 2 hydrogen bonds. So because of the extensiveness of hydrogen bonding in case of water molecule, water boils at 100 degree Celsius. Now methanol can form 2 hydrogen bonds. Likewise, even methylamine can also form 2 hydrogen bonds. But why the difference in the boiling point? The boiling point of methanol is around 65, while the boiling point of methylamine is around -6 degree Celsius. Now the difference in boiling point, though methanol and methylamine can engage in 2 hydrogen bonds, is because of the strong hydrogen bond formation in case of methanol and a weak hydrogen bond formation in case of methylamine. And this is because of greater electronegativity of the oxygen atom in comparison to nitrogen atom. And moving on to the impact of hydrogen bonding on solubility. Now polar molecules like ammonia, amines, alcohol and sugars are soluble in polar solvents like water by means of hydrogen bonding. So we are all familiar with the rule of thumb, that is like dissolves like. Polar molecules dissolve in polar solvents while non-polar molecules dissolve in non-polar solvents. So alcohols are soluble in polar water molecules by hydrogen bonding. So alcohols tend to interact with water molecules by hydrogen bonding. And therefore polar alcohol molecules are soluble in polar water molecules by means of hydrogen bonding. So when you pour alcohol into water, you'll get a clear solution. Alcohol freely dissolves in water. Because of hydrogen bonding. And even a solid substance like glucose, which is polar in nature, is also soluble in water. So polar alcohol and glucose molecules dissolve in polar water molecule due to hydrogen bonding. So lower members of ketones like acetone, carboxylic acids like acetic acid, amines, alcohols and sugars are soluble in water due to hydrogen bonding. So it is the hydrogen bonding that leads to solubility of these organic substances in water. That is due to dipole-dipole interaction. Now carbohydrates, also called as sugars, They are soluble in water, again due to hydrogen bonding. But in case of sugars or carbohydrates, you will find that there are multiple hydrogen bond formation because carbohydrates are polyhydroxyaldehydes or polyhydroxy ketones. They have many hydroxy groups and therefore they are freely soluble in water because of multiple interactions or multiple hydrogen bonding. So sugars with many hydroxy groups are soluble in water due to hydrogen bonding. Now what about the impact of hydrogen bonding on the viscosity? Now viscosity is the resistance of a fluid to flow. Put in simple terms, viscosity refers to the thickness of a liquid. So methanol and ethanol, they have one hydroxy group. Ethylene glycol has two hydroxy groups, while glycerol has three hydroxy groups. And what about honey? Now honey is more viscous and it is rich in sugars with water content. Now the major composition of honey is glucose and fructose. So around 38.2% of honey contains fructose and 31.3% of glucose is present in honey with water content of 17.2%. Now, as already mentioned, sugars are polyhydroxyaldehydes like glucose or polyhydroxy ketones like fructose. And because of the presence of multiple hydroxy groups, they tend to participate in multiple dipole-dipole interactions, that is hydrogen bonding. And because also water is one of the components of honey, they too participate in hydrogen bonding. So honey is more viscous than water due to hydrogen bonding. So what we see here is an increase in the viscosity as the number of hydroxy groups increase. As the number of OH groups increase, the viscosity increases because of hydrogen bonding. So more the number of hydrogen bonding or dipole-dipole interaction, it holds the molecules together, resulting in a strong intermolecular force and ultimately leading to high viscosity. So in case of ethanol, there's only one hydroxy group and therefore you find only one dipole-dipole interaction. Whereas in case of ethylene glycol molecule, which contains two hydroxyl groups, it can form two hydrogen bonds, making it stronger than one hydrogen bond as in case of ethanol molecule. But in case of glycerol, you find three hydroxy groups, which can form intermolecular hydrogen bonding, making it much stronger. So each glycerol molecule with three hydroxyl groups can form three hydrogen bonds, making it much stronger. Now in case of sugars, as they have multiple hydroxy groups, they participate in hydrogen bonding. And the water content in honey is an added advantage, resulting in increasing multiple dipole-dipole interaction, making it more viscous. So as the number of intermolecular forces increase, it increases the viscosity of the organic substance. So water, methanol, ethanol, ethylene glycol and glycerol, they're all viscous due to hydrogen bonding. So the substance with the possibility of multiple hydrogen bonding is more viscous, like in case of honey. So honey is more viscous than water because of high sugar content of glucose and fructose. And it is the hydroxyl groups in sugars that participate in multiple hydrogen bonds with water and each other, resulting in a strong hydrogen bonded interactions. Now the impact of hydrogen bonding on the vapor pressure. Now the molecules on the surface of liquid, like in case of water, they tend to escape from the surface in the form of vapor in the gas phase, and the vapor in the gas phase exerts certain amount of pressure, which is called as the vapor pressure. So intermolecular force between water molecules leads to low vapor pressure. So because of the cohesive force between the water molecules cannot escape the surface of the liquid that easily. So as the intermolecular force between the molecules increase, high energy is required for vaporization of the water molecules. And this leads to lower vapor pressure, and ultimately the rate of evaporation of water molecules goes down. Now what about the alcohol molecules? Even alcohol molecules, they tend to participate in hydrogen bonding. They tend to interact, like in case of water. And the bond energy is same both in case of water and alcohol. That is 21 kilojoules per mole of energy is required to break this hydrogen bond between the water molecules or alcohol molecules. So though the bond energy is same in case of water and alcohol, they differ in the boiling point. So water boils at 100 degrees Celsius while ethanol boils at 78 degrees. But the intermolecular force is one and the same, that is hydrogen bonding. So the difference in the boiling point is because of the difference in the vapor pressure. So water molecule with a vapor pressure of 2.8 kilopascals is less than that of ethanol with a vapor pressure of 6 kilopascals. So because of the high vapor pressure of ethanol, it is highly volatile. It evaporates easily because of a greater vapor pressure as compared to water. So the vapor pressure of a liquid or solid is directly influenced by the intermolecular force acting between its molecules. So when these forces are stronger, the rate of evaporation decreases, resulting in a lower vapor pressure. And what about the impact of hydrogen bonding on surface tension? Now surface tension is a fundamental property of liquids, explaining the water droplet formation. So water droplets on the leaf and waxed floor, they maintain a rounded shape with smallest possible surface area. And this is because of a phenomenon called surface tension. So let's find out why water maintains a rounded shape with smallest possible surface area. Now, water molecules on the surface of the water droplet, they are pulled sideways and downwards. So water molecules on the surface of a water droplet, they are pulled sideways and downwards, but not upwards, because there are no molecules on the top of the surface of water droplet to pull it upwards. While the water molecules at the center, they are equally attracted in all the directions. So water droplets on a leaf and wax floor maintain a rounded shape with smallest possible surface area because of the hydrogen bonds. So water molecules are held together by a strong cohesive force, that is hydrogen bonds. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.